Secret Engineer: How Emily Roebling Built the Brooklyn Bridge by Rachel Dougherty. Emily Warren was a bright, shiny spark who loved to learn. In time, she married a spry young engineer named Washington Roebling, whose mind was just as hungry as hers. The Roebling family built bridges. Washington's father, John A. Roebling, was considered one of the greatest engineers of his time, and now he had a risky new idea. Like many girls, she studied sewing and piano. Unlike many girls, she also studied math and science. He told Washington and Emily he had designed a bridge to span the quick whirling waters of the East River and to finally link Manhattan and Brooklyn. He planned to build 2 colossal towers and sling a 14,000-foot web of steel cable between them to create the grandest avenue the world had ever seen. John wanted to send his son to Europe to learn about new technology for building bridges. Emily insisted that she would accompany him. In Europe, Emily and Washington explored historic towns, tasted new foods, and studied the most recent advance in bridge building, the caisson. Caisson is like a giant open box turned upside down and sink into the water. The opening at the bottom traps air as the box sinks, so it's dry inside. This allows workers to dig deep into the riverbeds to find solid rock to build upon. These caisson, once fixed to the firm bedrock, form a sturdy base for the bridge's towers, strong enough to support the structure's weight. Emily and Washington hurried back to New York, buzzing with discovery. Workers in the caisson break boulders and shovel mud, digging deeper towards the solid river bottom. That's where they are. Wagons move mud and rocks from the riverbed to the barge, so from bottom all the way up. John wove 2 caissons into his design and prepared to build the Great Bridge, but he died before the construction began in 1870. Washington would have to take over as chief engineer. The caissons were larger than any ever made. The base of each one measured about 17,000 square feet. Just building them seemed nearly impossible, and that was only the beginning. Workers build the caissons on dry land. Then they carefully float their airtight container out onto the river. Once the caisson is in place, the workers sink it, displacing the surrounding water and trapping air inside. When it reaches the river bottom, workers can descend and start digging. As the workers dig, the caisson drops. Eventually, they dig past the soft riverbed and reach solid rock. Workers then fill the caisson with concrete and build the bridge's tower on top. Washington soon discovered that construction inside the caissons was muddy, dark, and sweltering. After hours in the caissons every day, he returned home aching and dizzy, but he pressured on. Washington drew plans late into the night, with Emily by his side. Emily heard that some of the workers were falling ill with pain, weakness, and nausea. They called it caisson sickness. Then, in 1872, Washington, like many of his workers, collapsed on the dock, and he had to be ferried back home to Brooklyn. Weeks later, Washington still couldn't get out of bed. Emily insisted she'd be his eyes and ears, and legs, and arms. As Washington's eyesight dimmed from the caisson sickness, he dictated instructional letters to Emily, and she read construction reports to him. Washington could breathe a little easier, knowing Emily would be at the worksite. But Washington's words felt clunky and confusing. When Emily repeated them to the engineers, she faithfully copied the terms and equations, but they seemed like a foreign language. She was nervous. Construction on the bridge was only just beginning, and there was so much she didn't know. So Emily started to read. She studied bridge engineering and learned from Washington and the assistant engineers. As she studied, the mechanics of the bridge became clearer. One set of cables would be strung between the tops of the towers. They would balance the pull of the other cables. That would lead from the towers to the anchorage blocks at either end of the bridge. The cables create the tension force, and the tower creates the comprehension force. A force is an invisible push or pull that acts on an object and together. These opposite forces would hold the deck upright. The main parts of the bridge were the towers, the cables, the deck, and the anchorage blocks. The towers, the cables, the anchorage blocks, and the deck. The more Emily learned and the more confident she felt. As time went on, she could see the drawings coming to life. She saw the steel cables swooping between the towers in what she'd learned was called the catenary curve, the perfect natural arc of a cable held only at its end, like a clothesline or a jump rope. She saw the tiny ink scratches she'd squinted at on paper transform into huge vertical cables called suspenders, which would shift the weight of the bridge deck to the main cables. She grinned, knowing that each suspender could hold 70 tons. Emily learned that the Roebling design for the bridge required a new method of steelwork that had never been used before. Cables were spun from thousands of thin steel wires twisted together like invisible yarn. The rigid deck platform was steadied with steel stays, cables that stripped down diagonally from the tower like sunbeams. With the tower and the deck, each diagonal line formed a triangle, the very strongest shape. No steel mill had ever been asked to make steel cables like these before, and the manufacturer wanted to meet with Washington to make sure they understood the plans. But Washington fretted. If word got out about how sick he was and that a woman was in charge, the project would surely be taken away from the Roeblings, despite all their work. Emily understood his concerns, but she insisted she could handle it. And when the meeting was done, she answered all their questions perfectly. Higher than average water, 110 clearance to waterline, 276 foot and 6-inch to waterline. Bridge deck is stiffened by triangular plates at each stay point. Diagonal stays steady and strengthens the deck and carries parts of its weight. Vertical suspenders transfer the weight of the deck to the main cables. Diagonal stays steady and strengthens the deck and carry part of its weight. 4 main cables carry the weight of the superstructure. That's everything attached to the towers. Vertical suspenders transfer the weight of the deck to the main cables. More than 10 years had passed since Emily had taken the reins, and the bridge was nearly built. She saw the main cables stretching across the wide river. From her window, they looked as delicate as spider silk, but she thought proudly of the equations she'd studied to calculate the cable's strength. If you're enjoying this book and you want to know how it ends, please have your parent click the link below to learn all the secrets of engineering. Until next time, bye.